Good morning to everyone. Good morning. Yes. Okay. So good morning. Good morning to everyone. So what we will do is whatever we have discussed in the previous class, few points I will explain. Can anyone tell me or can anyone give me some points what we have discussed in the previous class? Hmm? Okay. So can anyone tell me what we had discussed in the previous class? Hmm? Wow. We have discussed or we have solved some of the problems and we started with crystalline defect, Manjushri. Okay, fine. So we started with even Bharat Reddy. We have started with crystalline defects. Fine. So before that we have solved some of the problems. So have you practiced more problems? You have to, because on those concepts you can expect the question definitely in your board exam and even in your competitive exams, whether it is NEET or IIT or CET, whatever it is. Definitely you can expect the question. Fine. So then when it comes to crystalline defects, okay, before that, can someone tell me equation which talks about density of a unit cell? Can anyone? So that is density is equal to number of atoms, right? So number of atoms present in that particular unit cell multiplied by molar mass of that particular molecule or atom, right? So divided by volume of that particular unit cell multiplied by Avogadro's number. So this is where we have the density of a unit cell. Fine. So very important equation with respect to your exam point of view. Okay, with respect to your exam point of view. Please remember this equation and also practice the relation between A and R with respect to different types of packing. You have to practice. Anyway, for board exam, it may not be much important that equation, but for competitive exam, it will be important. Fine? But for board exam, whatever equation we had written just now, that is very important. So we will move to the next part. In crystalline defects, already we have discussed about vacancy defect and interstitial defect. That's what we have discussed. Vacancy defect and interstitial defect. Now when I am talking about vacancy, normally when a solid is heated, there is a chance that some of the atoms or molecule might be escaped. So then it will lead to the formation of vacancy. In the name itself it is there. There will be a vacant area in that particular solid. So naturally density has to be decreased. So therefore there will be decrease in the density, because for a particular area or volume, not area, for a particular volume there will be less number of atoms which will be present in case of the vacancy. So what will happen to the density? Density has to decrease because density is equal to mass by volume. Here volume is remaining same, but mass is getting decreased. That's where vacancy defect. Now when it comes to interstitial defect, so naturally, since there is the entry of new atom or molecule into that particular location, naturally it has to increase. It has to increase the density. That is interstitial defect. So both belongs to point defect. Both belongs to point defect. Right? So we have two types of defect. One is line defect and another one is point defect. Now whatever I have discussed, that is point defect, and in your syllabus we have only point defects, no need to worry. Fine. So that's what we have discussed in the last class. Now when I am talking about ionic solids, that's where they have bit different character. When it comes to ionic solids, now all of us we know NaCl crystal can be the example for ionic solids. So that's where we have the Cl minus, Na plus, Cl minus, Na plus. So like that, in case of the ionic solid, there will be presence of positive and negative charge. So one thing is sure that for every cations, we should have respective anions. For every cations, there will be presence of respective anions. So then only the ionic solid can be existable. Right? Then only there will be existence of the ionic solid. So what I mean to tell here is, there should be proper maintenance of stoichiometry. There should be proper maintenance of stoichiometry with respect to number of cations and number of anions. They should be equal. There is no question of anion might be more and cations will be less. No. Right? So that's where we have very important point. So unlike regular solids, non-ionic solid, where I have told that when you heat that solid, some of the atom might be escaped. So that cannot happen so easily here. If at all they are escaping, equal number of anions and cations should be escaped. Yes or no? Otherwise, the whole crystal structure will be collapsed. That's how the importance of the ions with respect to ionic solids. All of you have understood? Now, whatever vacancy defect or whatever interstitial defect in general we have discussed, if you want to specify it for the ionic solids, then we will be calling it as Frontal Defect and Schottky defect. Fine? See, for example, first we will very important for your exam point of view. So first one is Frontal Defect. Naturally, it is meant for the ionic solids. Or it's a crystal defect with respect to ionic solids. Now, can any one of you tell me, among the ions, we have two types, anions and cations. Among the ions, which will be of larger ionic radius? Anions or cations? So naturally, anions will be of larger radius because it has accepted electrons. So electron charge or electron number is getting dominated over the proton number, right? So therefore there will be expansion of the element will take place because number of proton is remaining same. Don't go with periodic table. Many people they will get confused. So even in periodic table when you move from left to right, so there is an increase in the number of electron. But why the hell atomic size is getting decreased? Because there even proton number is increasing because atomic number is getting increased. But here that is not the scenario. Say for example, if I take Cl minus atomic number is same. All of us we know atomic number is same, it is 17. But when it comes to number of electron, it has increased. It has become 18. So therefore, since proton number is remaining constant, that is atomic number is remaining constant, but number of electrons are getting increased, they are going to dominate. So due to that, there will be expansion of the ions will take place. So anions will be of larger size, cations will be of smaller size. So therefore, if I take a solid, means crystal, ionic crystal, so where I have smaller ion, larger ion, smaller ion, larger ion, like that it will be arranged. So that's how these ions will be arranged. Fine. Now, due to some condition, like heat or maybe some electric field or whatever it might be, due to some condition, there will be movement of ions will take place. There will be movement of ions will be taking place. So can you tell me which ions can move? Because we have positive, negative, positive, negative, positive, negative. So that's what we have, the positive and the negative ions. So my question here is very simple. If that is the case, which ion has to move? Whether positive ions has to move or negative ions? Yes, Purnima. Naturally, those ions which are smaller, because they can pass through the small space. So those ions which are smaller, they can move here and there. Because for a movement of anions, space is small. So anions cannot move here and there. It will be the cations. So there will be movement of cations. There will be movement of cations. Now what will happen? So there will be anions which is remaining same. Anions which are remaining same. But there will be dislocation. There will be dislocation of cations. There will be dislocation of cations. That's what it will happen. Fine. Okay. So that's what it will happen. Now what is happening? There is a vacancy. There is a vacancy at original place. There is a formation of vacancy at this particular point. But at the same time, there is a entry, interstitial point. There is an entry of cation. Extra cations are present. So what I mean to tell here is, in this case, we can see there is a formation of vacancy at original place, and we can see there is a formation of interstitial defect at new place where cation has moved. All of you will agree? So where cations have moved. Now Archit, conductivity increases, sir. Naturally, since there is a displacement of ions, it has to happen. But as a crystal, all of us we know that as a crystal, ionic solids are non-conductors. Ionic solids are non-conductors. But here what is happening, due to the cations coming close to each other, there might be repulsion, but as such, overall conductivity cannot be so much high. Okay, but when you fuse it, then yes. But since there is a movement, there might be some amount of conductivity which can be showed by this defective ionic solid compared to this one, because there is a movement of cations. Now what will happen? Cations, they will be repelling. That's where it will happen. Now what I mean to tell here is, there is a vacancy and there is a interstitial ion which has been formed. Interstitial ion, that is cation. Naturally that should be cations. Fine. Now since this will happen due to the dislocation of cation, it can also be called as dislocation defect. Fine. This can also be called as dislocation defect. That's where we have the Frontal defect. Now, can anyone tell me what will happen to the density of the crystal, what will happen at the end? So this is an ionic crystal and that is a defective ionic crystal. So what will happen to the density? Whether it has to decrease or it has to increase? Anyone? So density will not be changed. Density will remain same. Archit, no. Okay, fine. So Archit, so density will not change because I am talking about this particular volume. Please don't get confused. So it will remain same. Yes, Purnima. Why I am telling? Because I am talking about this particular volume. Right? So since I am talking about that whole volume, I can tell that density will not change. But if I go with this particular volume, definitely there is a decrease in the density. If I take this particular volume, definitely there is an increase in the density. But as an overall crystal, if I see, there is no loss of cations, there is no loss of anions. Nothing. They are there only in the crystal structure itself. So total number of cations, total number of anions, before and after, they are constant. There is no change. So therefore, in Frontal Defect, density is remaining same. Density will remain same. Okay, there is no change in the density. So don't get confused. Yes, if you take only this part, of course there is a decrease in the density. If you take this part, of course there is an increase in the density. But since we are talking about ionic solids, as I told, there should be equal amount of cations and anions. If I take only this area, then there is an imbalance. There is no stoichiometric balance. Right? There is no stoichiometry. So therefore, when it comes to Frontal Defect, there is no difference in the density. Fine? And Frontal Defect can also be called as dislocation defect. Frontal Defect can also be called as dislocation defect. Any doubts? Any doubts? Okay. Now, when I am talking about ionic solids, all of us we know there will be difference in the ionic radius. They cannot be same. Okay, actually. So there should be difference in the ionic radius. If they are remaining same, if radius is almost the same, then they cannot be ionic solid. They can form covalent, right? Since there is a difference in their ionic size, since they are ions, there should be difference in their radius. Now, according to Fajan's rule, first year we have discussed, right, chemical bond. I have two types of ions, means ionic solids. In one case, this is where I have the anion, this is where I have the cations. Now, in another case, I have the anion and I have the cations. So what you can observe, both are ionic solids, no doubt. Both are ionic solids where we have the anion, cations, anion and cations. But what is that you can observe here? Okay. Mayank is telling size of the cations. All of you will agree? Even that's what even I can see here. When it comes to the difference in the ionic radius, when it comes to the difference in the ionic radius, so that's what we can see, that difference is less here. Here, difference is more. Difference in the ionic radius is more and difference in ionic radius is less. In second case, all of you will agree? Now, can you tell me which type of cations, what I mean to tell you is, which type of metals they can show this type of one and which can show this type of one. Because in the periodic table, non-metals are dominating, right? Means metals are dominating. Now, in the metals, we have different category. Transition metal, S block elements. So in that way I am asking which category, which type of metals will come here, which type of metals will come here, because metals will also always go with the positive. It will have the cations. So which type of metal you will feel? Where this type of metal ions, which is that metal, and which is that metal which will form this type of cations? Can you tell me? Any one of you? First. Naturally, in the periodic table, when you are moving from group 1 and when you are moving towards the rightward direction, when I am facing the board, imagine this board as a periodic table. Now when I am moving from left to right, atomic radius is going to decrease. Atomic radius is going to decrease. That's where I have the alkali metals, which will be of larger size. So that's where I have the transition metal, which will be quite smaller in size. Which will be quite smaller in size. So now I can tell that whenever I am talking about a large difference in the ionic radius, whenever I am talking about a large difference in the ionic radius, normally it will be the transition metals which will be dominating. Alkali metals, no, it will be transition metals which will be dominating. Whether all of you are understanding? Because already as a metal they are of smaller radius. Already as a metal they are of smaller radius. Yes, Sarchit. Zinc and silver, etc. Yes, very good. So therefore, when they lose the electron, they will become much more smaller. Right? So that's where I can see NaCl, alkali metal. Na is alkali metal. So I can see positive and I can see chloride. But if I take silver chloride, so that's where I can see positive, that's where I can see negative. So what I mean to tell you is chloride is common. So chloride is common in sodium chloride also, silver chloride also. But cations are different. Here it is alkali metal. Here it is a transition metal. So therefore I can see large difference in the ionic radius over here. I can see large difference in the ionic radius. Right? So whether all of you are understanding? As Archit has written, yes, zinc, silver and all, they will belongs to this type of category, where they will form chlorides or any other ionic solids where cation size will be small, much small, and anions will be larger. So due to that, there is a large difference in the ionic radius. All of you have understood? So therefore, since the size of the cation is much smaller, they can easily show the Frontal defect because they can move here and there within the space which is available in an ionic crystal. So therefore, when it comes to Frontal defect, so these type of ionic solids are the one which can show the Frontal defect. Which type? Which has the large difference in there, which has the large difference in ionic radius with respect to cations and anions, difference in the ionic radius. Those type of solids will have the Frontal defect. That is quite natural because since I have large sized anions where cations can move here and there easily. Cations can move here and there easily. So that's where I can see the large difference in the ionic radius. So in that way I can tell silver chloride, silver iodide, silver bromide, even zinc sulfide, all of them, they can show the Frontal defects. Examples you should remember. Whichever is there in your textbook, that only I am giving, and on that only they will ask. Don't worry. So when it comes to the Frontal defect, silver chloride, silver iodide, silver bromide, and even zinc sulfide, as Archit had written. So silver and zinc, yes, in this case silver Ag plus. Silver is Ag plus, but zinc is plus 2, right? So that's where we have the cations. They can show the Frontal defects easily. All of you have understood? So why these ions will show the Frontal defect easily? Because large difference in their ionic radius. Why there is a large difference in the ionic radius? Because much smaller size of the cations. Because much smaller size of the cations. Those are the ones which can show the Frontal difference. Fine? All of you have understood? So we will move to the next one. Okay? So next one is Schottky defect. Even this is very important. Next one is Schottky defect. Frontal defect we have done. That is for ionic solid. Even Schottky defect is meant for the ionic solids. That's where we have the Schottky defect. So I think students will be having some affinity towards this name. Scotch. Not like that. Simply I told, that's why we have the Schottky defect. Fine. Even this is belongs to the ionic solid only. This defect also related to ionic solid. Now here what will happen? We have the cations and anions. So we have the cations and anions. Okay. Okay. So that's where we have the crystal. Now, that's what, maybe because of some heat or transmission of electric, this one, whatever it is. Yes, Sarchit, you are right. So whatever it is. Now what will happen? There will be some ions which will be lost. There will be some ions which will be lost. So due to that, what will happen here is, so what is happening? They can be neighbors or they can be a bit far, whatever it is. Now what is happening? There is a losing of one cation and one anion, as Archit had told. So there is a loss, in this case there is a loss of one cation and one anion. So there is a formation of two vacant sites. So one is meant for the cation and one is meant for the anion. Two vacant site has been created. Unlike regular solids, where I told vacancy can be of one ion or one metal atom, or it can be more than one metal atom. But here it should be equal number of cations and anions. Sir, for Frontal defect the coordination number ranges from 3 to 4. Okay, fine. So that is because of the smaller size, but even that will be decided by the ionic radius of anions. Okay, so that will be depends, coordination number depends on the ionic radius of the anion especially. If it is too large, then coordination number might be less. Fine. Anyway, we will not discuss on that. So that's where we have the equal number of anions and cations has been lost. So that's where we have the Schottky defect. That's where we have the Schottky defect. What I mean to tell here is final stoichiometry is maintained. It's not lost. So equal number of anions and cations are maintained. So that is very important. Now can you tell me what will happen to the density? What will happen to the density? So density is going to decrease. There is a drastic decrease in the density. So So there will be decrease in the density, no doubt. Yes, Archit, there will be decrease in the density because ions are lost. So less ions in this volume, more ions in this volume. So since there is a decrease in the ions involved in that particular volume, so density has to be decreased. But in Frontal defect it was remaining same. But in Schottky defect density is getting decreased. All these points you should remember. Now, if you observe here carefully, I have maintained ionic radius of these two. Difference is there, but less difference is there, right? So that is because Schottky defect will be shown by those ionic solids, especially with those ionic solids which are having alkali metals or alkaline earth metals, which will be having alkali metals or alkaline earth metals. That's where we have NaCl, KCl, even cesium chloride. They all belongs to this category. They all belongs to this category. But yes, Archit, so there will be difference will be there in ionic radius, but not much difference. Okay, difference should be there, but not much difference. As he has told, as Archit is writing, there will be comparable difference. Means difference is there which we can observe, but not high difference. Okay, so these are some of the examples. But we have one of the ionic solid which is there in your textbook also. That is silver bromide. That is silver bromide. So the speciality of this particular ionic solid is it can show even Frontal defect also, even it can show Schottky defect also, which is that one silver bromide. But otherwise they are restricted. Alkali metal involved ionic solids, it will go with Schottky defect, and transition metals involved ionic solids, they will go with the Frontal defect. That is a common observation. But there are some exceptional cases like silver bromide, so which can show both Frontal defect also, Schottky defect also. All of you have understood? Any doubts? So these two are very, very important for your examination point of view. Fine. So now we have impurity defect. Impurity defect. So one of the best example is semiconductors, doping. One of the best example for impurity defect is semiconductors. But anyway, I will discuss that one later. Impurity defect means we have one ionic crystal. Now before crystallization, when you fuse it at high temperature, when you fuse it, before going for solidification, if you add some other ionic solutions, now once again if you mix that one and if you make them to make a crystal, now what will happen? It has to maintain equal positive and equal negative. So due to that, some of the cations or anions, it will be displaced by another cations. That's why it is called as impurity defect. Please remember, cations can be displaced by cations only. Anions will be replaced by anions only in case of the impurity defect, especially with respect to ionic solids. Otherwise, whatever gold ring I am wearing, it is an impurity defect, where gold has been mixed with the copper. Whatever alloys we have, they are all impurity defect, because where different elements are mixed together in that particular solid. That is a general example. But when it comes to ionic solids, impurity defect, if you want to go, I have NaCl. I have the NaCl. This NaCl I am going to mix with the strontium chloride. I will take the example which is there in your textbook. I am going to mix with the strontium chloride. Strontium prefers to have the +2. So naturally strontium chloride. when they are mixed together. Okay. Now, as a ionic solid NaCl, what will happen in case of the NaCl? We have Na plus Cl minus, Na plus Cl minus. Like that, it will be arranged. Right? But when they are mixed with strontium chloride, when they are mixed with strontium chloride, anions are same. Both are chlorides only. But if you see the cations, strontium plus 2, right? Strontium plus 2, sodium plus 1. So therefore, what will happen? Here there will be minus, like that it will be done. Now what is happening? If you observe here carefully, one strontium is making 2 sodium to be lost. One strontium is making 2 sodium ions to get lost. Why? Because net charge should be 0. That's what I told, equal number of anions and cations, right? Since strontium is plus 2, sodium is plus 1, so one strontium can displace 2 sodium ions. So that's what is happening, right? So as NaCl, that's where we have Na plus and Cl minus. But when it is mixed with strontium chloride, now 2 Na plus are getting displaced.
So 3 got displaced, right?
3. No. Oh no. Sorry. So 2 Na plus is getting displaced. Yes, originally here and 1 here. Fine. So that's where we have the impurity defect. Even semiconductors, preparation of semiconductors, which we are going to discuss and which is very important. I think, yeah, here it is not there. So that is also an example for impurity defect. Even alloys, preparation of alloys, where one type of elements will be mixed with another type of elements. That is also an example for impurity defect. But they are purposefully done. They are purposefully done for the application. They have their own application. Fine. So all of you have understood. That's where we have the impurity defect. Any doubts? So shall we move to the next one then? Yes, N type and P type. That's what I am not discussing here. According to a textbook only I will go. But you can give the example, that one as impurity defect. Fine. So we will move to the non-stoichiometric defect. Non-stoichiometric defect. Next one is non-stoichiometric defect. Now, when it comes to non-stoichiometric defect, one of the important one here is metal excess defect. One of the important one here is metal excess. Since we are dealing with non-stoichiometry, naturally there should be difference in the element ratio. There will be difference in the element ratio of that particular solid. It can be ionic solid or any other. So we'll go with ionic solid. That's where we have the metal excess defect. So whatever I will be telling now, it is very, very important for your exam point of view. I have NaCl. Okay, I have NaCl crystal, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus. So I have the ionic solid. Now what I will do is, I will heat this ionic solid in the presence of sodium. In the presence of sodium. Now due to that, what will happen? Some of the sodium, they will come and they will attach to the surface of this particular solid, ionic crystal. They will come and attach to surface of this particular ionic crystal. Now, due to that, what will happen? These sodium, they are ready to donate the electron. They are ready to lose the electron. All of us we know. compared to Na plus is stable, right? So therefore this sodium tends to lose the electron, right? So due to the attachment of the sodium on the surface, some of the inner chloride ions, they will start moving towards the sodium. They will start moving towards the sodium. But during that time, when they interact with the sodium, they are going to lose their own electron. Excess electron, whatever chloride is having, they are going to lose that excess electron because this sodium is ready to donate the electron to chlorine. Now due to that, what will happen? There will be formation of Na plus, and Na plus. So here also Na plus, so Cl minus, Na plus, so another Cl minus, so here electron, so Na plus, electron, Na plus, electron, Na plus. So that's what is happening. So whatever chloride was here, it has moved here and it has lost the electron. So therefore, Na plus Cl minus, Na plus Cl minus, so total ratio, it is getting altered. Chloride is same, Na plus is getting increased, but Na plus is not present in the ionic crystal, they are present on the surface. Now whatever chloride place is there, it is taken over by the electron which has been released by these chlorides. It has been released by these chlorides. All of you have understood? Now there is a presence of free electrons. There is a presence of free electrons. So due to the free electrons, all of us we know, free electrons can be easily excitable. When they come back, they will release the different wavelengths of energy. They are easily excitable. But when they come back, they can easily release the energy. That's where they can give the colors. That's where they can give the colors. That's where we have lithium chloride, which will give the pink color. If I take potassium, they will form lilac color, or I can tell lilac. Lilac means purple type, purple or violet color. That will be common, violet color. So that's where due to this particular condition, some of these ionic crystals, they can have the colors when they are exposed to the visible light. That is because of the availability of the free electrons. Okay, actually, yes, I was not getting that particular color. Okay, violet, okay. Okay, light purple color we can tell. Yes. So that's where we have the condition. Now, these centers where free electrons are there, they are called as Farbengenter or F center. Farbengenter or F center. That's where we have the important word. Okay. So F center is because of the metal excess defect. So when it will be formed whenever there will be heating of ionic solid in the presence of the respective metals. Okay? Yes, that's where we have the Farbengenter or F center, because of which there will be colors to the ionic crystals. It's very important. 1 mark question they have asked many times. Please remember, metal excess defect, especially Farbengenter center or F center, they have asked many times. So that's where we have one of the very, very important metal excess defect. All of you have understood? So why F center has been formed? F center has been formed due to the metal excess defect. How this F center has been formed? When a metal or ionic crystal is heated in the presence of the vapors of the respective metal, now there will be losing of electron by the anions to gain the electron by those new metals which is present on the surface, right? So those free electrons are the one which will lead to the formation of F center, or it should be called as F center. Very important. Yes, Archit, I will be telling that one now. Okay, especially zinc chloride, I will be telling now. Now I have zinc oxide. Sodium chloride, yes, it will be yellowish in color. Same way we have the zinc oxide. Sir, sodium chloride, when it is yellow, whatever sodium chloride we have, it is white. That's what the question, right? But when you heat it, now you can observe. Okay, now? So now we have the zinc oxide. Now when you heat the zinc oxide, now normally it will be white crystal. Zinc oxide will be white crystal. But when you heat it up, there will be liberation of oxygen. And there will be formation of free electrons. So due to that, now we can have a non-metal which is getting liberated, which is a gas, and a metal is present as a metal ions in the solid itself. So therefore even it can be an example for metal excess defect. Right? So only some of the zinc oxide it will do like that. So as a whole zinc oxide crystal, now it will get turned into yellowish color. Not all zinc oxide will be turned. Some of the zinc oxide in that particular crystal structure, it will get converted into zinc plus 2 and oxygen. So due to the liberation of oxygen, now what will happen? There will be excess of zinc ion which will be present in that particular crystal structure, and during the process there will be formation of free electrons. So that's where we have another example for metal excess defect. And due to the presence of free electrons, it will have the yellowish color. As a zinc oxide in its native form, without heating, it will be white in color. Okay, white color solid. But when it is heated up, it is becoming yellowish color. The reason is due to the formation of or liberation of free electrons. So from where that free electron came? That free electron came due to the liberation of oxygen gas. All of you have understood? So that's where we have the condition. Yes, that's where we have the visible, which is visible with respect to these ionic solids. All of you have understood? But please remember F center, Farben Genter center. That one you should remember, metal excess. Okay? And when it comes to vacancy or interstitial, better to remember is Frontal and K Defect. All of you have understood? Now another one example for non-stoichiometric one is metal deficiency. This one you people might have studied in your first PU. This one you have studied in your first PU. If you go back, oxides of I'm not getting that word. Oxides of S block element, one particular oxide, non-stoichiometric oxide, they will form non-stoichiometric oxide. It's there in your first year, S block element. Same way we have oxides of iron, that is iron oxide is the best example for metal deficiency. According to this one, they should be iron and oxygen should be present in 1:1 ratio. But when they studied the structure, they found that iron will not be exactly 1. Overall, it will become 0.9 something and oxygen will be 1. Exactly 1 it will not be there. As a whole crystal, when they studied, the ratio is not exactly 1:1, where iron will be bit less in amount. So therefore it is an example for metal deficiency defect. But it is naturally present. It is naturally present in this form. Fine? So that's where we have the metal deficiency defect. Same way, that's what I am not remembering that one. S block only, we have non-stoichiometric oxides. Okay, we had non-stoichiometric oxides. Even that can be an example with respect to S block. Exact example I am not remembering. Fine. So that's where we have the metal deficiency defect. All of you have understood? Fine. So whether I will move to the next one. By this we have finished with the crystal defects. We have finished with the crystal defects. So in crystal defects, 3 are very important. One is Frontal Defect, another one is Schottky defect, and last one is Farben-Genter center. So these 3 are very important, but rest of the things also you have to read. But these 3 are very important. Fine? Okay? Now we will move to the conductivity. Now we will move to the conductivity. Fine? Now, when I am talking about conductivity, especially I am talking about electrical conductivity, right? Or electric conductivity. Now, whenever we are talking about metals, okay, so that's where we have the outermost electron. We will imagine we have a metal which has 4 electrons. And while explaining the metallic solids, I have told, which is nothing but electron C model, not SEE. Electron C model means SEA. Electron C model, which talks about metallic solids, how these metals, they are having metallic bond. So which is better explained by electron C model. So where I have told, when we have neighboring element, when we have the neighboring element, since we are dealing with large sized elements, whatever outermost electrons are there, since they are too far from the nucleus, okay, so they will be having less affinity towards the nucleus. They will have the less affinity towards the nucleus because distance is getting increased, right? So now at the same time, this nucleus is almost, don't go with my picture, okay? So imagine that distance from here to here and here to here, it is almost the same, okay? So imagine that distance from here to, that is 1, and distance from this nucleus to this nucleus, that is 2. So it is almost the same. So that's what I told, one particular Hindi word. So gali ka kutta na ghar ka na ghat ka. That's what I told, if I remember. So this electron will not exactly belongs to this nucleus. This electron will not exactly belongs to this nucleus, right? So therefore they are freely available. They are freely available or easily available for the electric conductivity. They can move from one end to the another end easily. That's where we have the electric conductivity comes, where there will be availability of ions or there should be availability of the electrons. Then only those material can act as a electric conductors. For example, if I take sodium chloride crystal, they are non-conductors of electricity. But same sodium chloride, if I put it into water, now they became very good conductor of electricity. Why? Because due to the availability of free sodium ion and chloride ion. So due to that, they have become conductors, good conductors. Iron rod, they are very good conductors of electricity. Why? Because they have the free electrons due to the presence of metallic bond. That is due to the presence of okay, Archit, I know bit Hindi, no doubt. Okay, I used to watch Hindi movies. Compared to, I am not against Kannada, but compared to Kannada, I used to watch Hindi movies. I'm watching Hindi movies only. I can speak Hindi very easily, Archit. Okay, na? Fine. So that's where we have the electron C model. Fine. Now that's where when I am talking about electric conductivity, it can be due to loosely bound electron or it can be due to freely available ions. Now we have another concept where they will tell that we have the electron. Still it is within the shell. Still this electron, it is within the shell, which is called as valence electron. Now I will provide the energy that can be in the form of heat. I will provide the energy. Now what will happen? This electron, it will be slightly excited to higher level. It is slightly excited to higher level due to the availability of the energy. But still, when we remove the energy, they can come back to its original state. I am talking about outermost valence electron. Okay? So now, this electron is there, since it is loosely bound to the nucleus, but still, they are within the shell of this particular element. They are not completely free electrons. Now, when you provide the energy, they can be excited, right? Where they are available for the conductivity now. But when you remove the energy, they will come back. But at present, they are available. This is called as conducting band. This is called as conduction band or conductivity band. Anything is fine. Now, what I mean to tell you is, this is where we have the valence shell. About this, based on the nuclear energy, about to some extent, element can be excited, but once you remove the energy, they can come back. I am not talking about inner energy level, I am talking about valence shell, right? So that's where we have the electron, it can come back. But if it is much more higher, it has more, then it will lead to the photoelectric effect, which is not available now. It is lost, that electron is gone. So that's where we have conductivity band and valence shell. As this difference will get decreased, now conductivity of that particular molecule will be increased. As this difference will be more, then conductivity will also become less. Fine? So no need to worry, don't get confused. So what I will do is, in the next class, we will discuss about N and P type of semiconductors. So don't worry about conductivity band, valence shell, fine, but don't worry. So what I mean to tell you is, there should be availability of loosely bound electron or free electron. If there is a presence of free electron, definitely a good conductors. If there is a loosely bound electron, then we have to provide some condition, then they will become a good conductors. Fine? So that's where we have the semiconductors, which under normal condition, they will be partially conducting the electricity. They are not very good conductors. But when you provide the condition, they can behave as a good conductors of electricity. That's where we have the semiconductors. Fine? Anyway, any doubts? We are going to continue in the tomorrow's class, and tomorrow definitely we are going to finish the solid state topic. Fine? So we are going to finish it tomorrow. Any doubts? Archit is feeling very happy by seeing the Hindi. Yes? Okay. Thank you very much. Thank you everyone.